Comets aren't supposed to grow. Yet, as scientists watch 3I/Atlas, an interstellar visitor discovered in July 2025, its coma ballooned, and the latest James Webb data suggests the core itself might be swelling in ways that defy cometary science. Standard physics demands these icy bodies shrink near the Sun, but Atlas has broken that rule, leaving experts scrambling to explain the anomaly. If James Webb reveals 3I/Atlas is growing, what strange force could be fueling the expansion, and what does that mean as it races toward Mars? The answer could upend what we know about the solar system, and it starts with a single, impossible measurement. Every comet begins as a small, icy body, adrift in deep space until gravity draws it toward the Sun. As sunlight streams across the surface, temperatures climb, and frozen gases, water, carbon dioxide, sometimes even exotic volatiles, begin to vaporize. This process, called sublimation, drives jets of gas and dust away from the nucleus, building a vast, glowing cloud known as the coma. The coma can swell to thousands of kilometers across, but it is always made from material lost by the comet, not gained. The more active the comet, the faster it sheds mass. Dust and vapor stream outward, sculpted by solar radiation and the solar wind into the iconic tail that points away from the Sun. Over time, this relentless erosion eats away at the comet's core. Each orbit strips away more ice and rock, leaving behind a smaller, weaker body. Some comets break apart entirely, their nuclei shattered by heat or tidal forces, scattering debris along their path. Others fade into darkness, their reserves of ice exhausted. No matter how spectacular a comet appears in the night sky, its fate is set by these physical laws. Growth, in the sense of gaining mass or swelling the nucleus, has no place in this cycle. Standard models predict only loss, never expansion. The coma's size and brightness are a direct measure of how much material is being released, not created. For centuries, astronomers have watched comets shrink and fragment as they near the Sun, confirming this pattern again and again. The expectation is simple. Every approach to the inner solar system leaves a comet smaller than before. Any deviation from this rule demands extraordinary evidence and a new understanding of cometary physics. The James Webb Space Telescope's infrared eyes locked onto 3I/Atlas in late July, pulling back a dataset that left the operations team unsettled. The coma's full width at half maximum, a technical measure of its spread, jumped by nearly 20% in just under 2 weeks. That's a rate of expansion unmatched by any Oort cloud comet at this distance from the Sun. Ground-based telescopes confirmed the trend. The apparent diameter of the coma ballooned from 50,000 to well over 150,000 kilometers, even after correcting for the comet's approach and changing phase angle. Meanwhile, the surface brightness profile remained sharply peaked, not diffusing as it would after a fragmentation event. Hubble's high-resolution imaging, taken days apart, showed no sign of new jets or chaotic debris, just a symmetric, steadily growing envelope of gas and dust. Attempts to fit the expansion to standard models of outgassing failed. The best thermophysical codes, even with carbon dioxide-driven jets and amorphous ice crystallization factored in, could not account for the observed speed or scale of growth. The nucleus itself, buried deep within the glare, remained unresolved, but dynamic mass estimates based on outgassing rates and coma brightness suggested a body far more massive than initial optical data implied. Some models, drawing on the James Webb Space Telescope's compositional spectra, placed the total mass over 33 billion tons, with a possible diameter exceeding 3 kilometers. Yet the numbers refused to stabilize. Every new observation deepened the puzzle. The coma's expansion was not a one-off outburst, but a sustained, measured process. No radar echo confirmed the nucleus size. Atlas remained too distant for even Goldstone's powerful beam. Instead, astronomers were left with a growing list of indirect clues: a coma that kept swelling, a nucleus that defied sizing, and a pattern of activity that didn't fit the rulebook. The data didn't just challenge expectations, they forced a reckoning with the limits of comet science. Comet modelers lined up the usual suspects. The first was hidden volatile reserves, deep pockets of carbon dioxide or water ice, sealed beneath the crust, suddenly exposed as sunlight crept in. Calculations ran the numbers. For the coma to swell this quickly, Atlas would need to vent hundreds of thousands of tons per day, yet every kilogram lost should shrink the nucleus, not inflate it. The mass balance refused to cooperate. Outgassing strips material away, and even the most volatile rich comet can only shed what it already carries. Next came fragmentation. If chunks were breaking free, the coma might appear to grow as debris spread outward, but fragmentation leaves a signature: ragged jets, asymmetric halos, a debris field marked by chaos and sudden jumps in brightness. Atlas showed none of these. Hubble's images stayed stubbornly symmetrical, with no evidence of stray fragments or sharp discontinuities. Then came the possibility of optical illusions, scattered sunlight, forward scattering dust, or instrumental artifacts mimicking expansion. Teams combed through the data, comparing phase angles, correcting for every known bias. The coma's growth rate held steady across different telescopes, wavelengths, and observing conditions. No trick of the light could explain the numbers. Each hypothesis was tested, modelled, and set aside. The standard playbook ran out of pages. The scientific process, rigorous and methodical, had closed every familiar door. What remained was a growing body with no clear mechanism, and a field of researchers forced to consider the unorthodox. Infrared data from the James Webb Space Telescope brought an unexpected layer of complexity to the Atlas mystery. Analysts working with the MIRI instrument sifted through a flood of raw flux measurements, looking for the telltale glow of heated dust and gas. What they found did not fit the usual solar-driven pattern. The coma's thermal signature showed regions of elevated temperature that did not align with the comet's sun-facing hemisphere. Instead, the hottest zones appeared at odd angles, sometimes flaring up during periods when direct solar input should have been minimal. In one sequence, a localized spike in infrared flux was recorded just hours after Atlas rotated away from peak sunlight, an anomaly that repeated itself with shifting locations over the course of several days. Attempts to model these hotspots as the result of delayed heat conduction or buried volatile pockets came up short. The observed timing and intensity required an energy source acting from within, not simply stored solar warmth leaking out. The usual suspects, surface outbursts, pressure vents, crystallization fronts, could not account for the persistence or the spatial pattern of the heat. JWST's compositional spectra confirmed the presence of abundant carbon dioxide and water vapor, but the thermal maps hinted at a process operating independently of the sun's steady hand. For the team at the Space Telescope Science Institute, these readings raised more questions than answers. Each new dataset forced a re-examination of what could drive such a sustained, off-axis release of energy. The possibility of an unknown internal mechanism, or even a process not yet described in comet science, hovered at the edge of every discussion. The puzzle was no longer just about mass or size, it was about energy, and the rules by which Atlas seemed determined not to play. Oumuamua arrived in 2017, a slender, tumbling fragment on a hyperbolic path. Its course bent away from the sun more sharply than gravity alone could explain. The official explanation, outgassing from hidden ices, never matched the data. No tail, no coma, no detectable volatiles, only a persistent, unexplained push, as if something inside was quietly changing its velocity. Neil deGrasse Tyson, on a late-night broadcast, called it the most alien object we've ever tracked. Michio Kaku, in a panel at Caltech, wondered aloud if we were seeing the first evidence of interstellar technology, then cautioned that extraordinary claims demand extraordinary proof. 2 years later, Borisov swept in. Unlike Oumuamua, Borisov looked and behaved like a classic comet: jets of gas, a bright, sprawling tail, all the familiar signs of volatile-rich ice meeting sunlight. Its activity was extreme, but within the bounds of natural models. Borisov's chemistry, tracked by dozens of telescopes, matched expectations for a visitor from the coldest reaches between stars. It was a relief, a return to the known. Now, Atlas, the third interstellar object and the first to combine the oddities of both predecessors. Its coma expands at a rate unseen in solar system comets. Spectra from the James Webb Space Telescope show a dominance of carbon dioxide, with water far behind, and a mass estimate over 33 billion tons that refuses to settle. The numbers are unstable, the models uneasy. Tyson, in recent interviews, points to the pattern, each visitor more disruptive, each anomaly more pronounced. Kaku, writing in Scientific American, frames it as a cosmic escalation, nature, or something else, sending ever stranger messengers through our neighborhood. Among astronomers, the question is no longer whether interstellar objects will surprise us, but how far the surprises will go. Each one has rewritten the rules. Oumuamua's acceleration, Borisov's chemistry, Atlas's apparent growth, 3 data points that trace a trend, not an accident. The sense of an unfolding pattern is hard to ignore. If this is a new normal, the implications reach far beyond comet science. What comes next may test the limits of what we think is possible in the solar system. Mars mission controllers watch the numbers with growing concern. As 3I/Atlas races toward its closest approach, the projected coma envelope swells beyond 300,000 kilometers, 4 times the typical extent for a comet at this solar distance. Models fed with the latest photometric and spectroscopic data push the dust flux estimates into uncharted territory. For micron-sized grains, the predicted impact rate at the coma's edge could reach 100 to 1,000 particles per square centimeter per hour. That's an order of magnitude above the worst-case scenarios drafted for previous Mars encounters, including the Siding Spring flyby in 2014. The thin Martian atmosphere offers little protection. Dust grains larger than 10 microns can survive entry, generating plasma sheaths or even reaching the surface. For orbiters, the threat is more immediate. Standard shielding is built for the background drizzle of interplanetary dust, not a sustained hail of particles from a hyperactive interstellar comet. Engineers at ESA and SpaceX update their risk matrices daily, running simulations to predict when and where the coma's densest regions might intersect with orbital paths. Contingency plans circulate, shifting spacecraft to higher, more shielded orbits, stowing sensitive instruments, powering down non-essential systems. The memory of Siding Spring lingers in every decision. Then, a brief spike in dust forced a fleet-wide reorientation, but the predicted flux was lower, and the event passed with only minor sensor degradation. Now, with Atlas, the unknowns multiply. The dust environment could fluctuate rapidly if the comet's activity surges, or it could plateau if the expansion stalls. Every new data point feeds a cycle of recalculation and debate. For surface missions, even a thin haze of fine dust could degrade optics and solar panels, or trigger false readings in atmospheric sensors. The possibility of millimeter-scale grains reaching the ground while remote cannot be dismissed. In the control rooms, the mood is tense. The stakes are not theoretical. Mars is in the crosshairs and the countdown to closest approach has begun. Avi Loeb, the Harvard astrophysicist known for challenging scientific orthodoxy, stepped into the debate with a proposal that unsettled even seasoned comet researchers. In an interview with Der Spiegel, Loeb described the possibility of a self-expanding structure, suggesting that 3I/Atlas could be actively deploying hidden components as it nears the Sun. "We must consider the idea," he said, "that an object could be engineered to transform itself in response to solar energy." Loeb pointed to the sustained growth of the coma and the persistent uncertainty in nucleus mass as evidence that natural explanations might not be enough. He referenced the energy requirements, noting that the observed expansion would need a power source far beyond what sunlight alone could deliver at Atlas's current distance. The concept of an unfolding mechanism, material stored compact, then released or inflated as the object heats, echoes through his public statements and technical papers. For Loeb, the key lies in the regularity and scale of the changes, not the chaos of fragmentation, but a measured, almost deliberate process. While most of the community remains cautious, the idea that Atlas could be more than a passive chunk of ice has entered the scientific conversation. The boundaries between natural and artificial have never felt thinner. NASA's public response to the Atlas controversy has been measured, almost clinical. In a September 18th press briefing, spokesperson Dr. Marissa Chen described the object as an active interstellar comet exhibiting high levels of volatile-driven outgassing, careful to avoid any language that might suggest novelty beyond standard cometary physics. Official releases refer to the growth as an apparent expansion of the coma and stress the need for further data before drawing conclusions. No mention of artificial mechanisms, no speculation on internal sources of energy. Behind the scenes, requests for more James Webb Space Telescope observation time and interagency coordination with Mars mission teams hint at deeper concern, but the official line holds. Independent researchers, less constrained by institutional caution, have been far more direct. Dr. Lionel Guzman, speaking at the American Astronomical Society's fall meeting, called Atlas's behavior fundamentally unnatural in the context of comet science. A preprint circulating among planetary scientists uses the phrase non-standard physical process to describe the sustained coma growth. Social media amplifies these words, fueling debate and public anxiety. The divide is clear. Agencies urge patience and more data, while outspoken scientists warn that the old models may no longer apply. The scientific community, usually unified in its language, now finds itself split, caught between caution and alarm, and watched by a public hungry for answers. 3 objects, 3 escalating mysteries. Oumuamua, silent and swift, left astronomers grasping for explanations. Borisov, volatile and bright, offered a brief return to the familiar. Now, Atlas, more massive, more active, and, by all current models, impossibly dynamic. The timeline is unmistakable. Each arrival brings a sharper break from expectations. Each anomaly outpaces the last. In late September, as Atlas closes on Mars, the question shifts from isolated oddity to pattern. Is this a statistical fluke or a sequence with intent? Tyson, speaking on a global webcast, calls it a cosmic drumbeat, growing louder with every pass. Kaku, in a radio interview, wonders if the solar system is being used as a test bed, a proving ground for phenomena we have yet to classify. The Mars flyby looms just days ahead, with the projected coma now wider than the planet itself. Every new dataset feeds the sense of escalation. No consensus, no closure. Only the certainty that the rules are shifting, and that Atlas is not the final word. The story is not finished. The next move belongs to the comet, or to whatever drives it. On July 3, 2025, 3I/Atlas became the 3rd confirmed interstellar object to enter our solar system. Unlike every comet studied before, Atlas's coma has expanded at a rate measured by JWST and ground-based telescopes that exceeds all standard comet models. Radar and thermal data have shown a sustained growth trend and localized heat spikes, with no evidence of the fragmentation or volatile depletion that typically explains such activity. Multiple mainstream hypotheses have been tested and ruled out based on mass loss calculations and the lack of chaotic debris. As Atlas approaches Mars, official NASA releases acknowledge the anomaly, while independent scientists use the term unnatural to describe its behavior. The mechanism driving this growth remains unclassified and unresolved. Today, the risk to Mars spacecraft is real, and the scientific debate continues. Atlas stands as direct evidence that our current understanding of interstellar visitors is incomplete, and the critical questions about its true nature remain open.